During the medieval Crusades, European knights marching into the Levant collided with Islamic forces wielding a highly unusual weapon. The swords carried by Saladin's armies had a distinctively wavy blue-gray surface. Returning soldiers brought back tales of weapons that could cleave a man in half and shatter heavy European broadswords on impact, yet remained flexible enough to bend from hilt to tip without snapping. Modern Damascus steel found in commercial knives relies on pattern welding, where a blacksmith manually stacks and folds different steel alloys to create a decorative finish. Historical Damascus swords were forged from solid, homogeneous ingots of high-carbon crucible steel called Wootz. The swirling pattern emerged organically from the internal chemistry of the metal. Understanding the performance of these ancient weapons requires looking past modern marketing and examining the undisturbed matrix of the original Wootz ingot. The supply chain feeding the Middle Eastern forges originated thousands of miles away. Ancient archaeological sites in South Asia, specifically across India and Sri Lanka, reveal a massive, scaled industrial operation. This cross-section illustrates the South Asian crucible method. Craftsmen loaded pure wrought iron into clay vessels, alongside specific organic matter. Catching intense monsoon winds, the furnace heat baked the plants, releasing concentrated carbon gas, represented by arrows diffusing directly into the solid iron. As the solid iron absorbed that carbon, its melting point steadily dropped. Eventually, the entire mass liquefied, spreading carbon evenly throughout the alloy. The crucibles were left to cool for days in the dying embers. The result was a small, dense, hemispherical cake of steel that was extracted and exported across trade routes to master artisans in Persia and the Levant. South Asian crucible steel was a product of precise chemistry, yet its lethality relied on a geographic accident hidden within the cooling metal. The iron ores mined in these specific regions of India contained microscopic trace impurities, most notably about 0.004% vanadium. As the liquid steel cooled over several days inside the crucible, it underwent a process called dendritic solidification. Massive, branching iron crystals grew into the liquid pool. Expanding, they pushed tiny vanadium atoms outward, locking those impurities into tightly clustered parallel bands. When the Wootz cakes arrived in Persia, the swordsmiths worked them within a narrow temperature window. They maintained the steel strictly between a dull blood red and a slightly brighter cherry red, gauging the heat entirely by eye. This repeated thermal cycling triggered a microscopic migration. The excess carbon gathered directly onto the hidden vanadium bands, organizing into flexible layers of microscopic spherical beads called cementite. This structure dictates the blade's performance through a mechanical concept called differential wear. This edge retention chart compares reconstructed Wootz against modern high-carbon steels. At a historically accurate lower hardness of 41 HRC, the Wootz heavily outpaces the modern alloys. When cutting through tough, abrasive materials, the softer steel matrix naturally erodes faster than the dense cementite bands. The steel functioned as an advanced, self-sharpening micro-serrated composite. The constant exposure of microscopic teeth kept the edge biting into targets long after a homogeneous blade would have blunted. Despite its immense value on the battlefield, reliable production of true Damascus swords ceased entirely by the late 18th century. A disruption in the raw materials supply chain caused the technology's collapse. The specific rock veins in India providing the essential vanadium were eventually exhausted. The ancient smiths operated by visual observation rather than an understanding of atomic chemistry. When they applied their strict thermal cycling to new, clean iron ores, lacking the impurities, the carbon clumped into massive, brittle networks. The watered pattern failed to appear, and the blades became unworkably fragile. The secret remained buried until 2006, when researchers at the Technical University of Dresden dissolved a sample from a genuine 17th century blade and placed it under a high-resolution electron microscope. This proposed nanostructure diagram shows their discovery of multi-walled carbon nanotubes hidden within the metal. These flexible carbon cylinders appear to encapsulate the brittle cementite nanowires, halting microscopic cracks before they could spread through the blade. When the chemistry of the ore changed, the master smiths of the Levant and Persia could not adapt. Their empirical mastery was tied to a localized geological anomaly they had no way to quantify. The Crusader myths of silk scarves severed in midair were likely exaggerated for drama, but the physical reality of the steel was a sophisticated feat of material manipulation. These blades prove that ancient artisans successfully managed ultra-high carbon nanocomposites. They achieved microstructural control over steel centuries before humanity possessed the scientific language